State-of-the-art agentic memory systems are built to execute tasks. When applied to intimate, long-term relationships, those same systems fail. High-precision factual retrieval is efficient for searching documentation or writing code, but relationships run on emotional context, behavioral patterns, and gradual evolution, dynamics that keyword matches cannot capture. The architectural contrast is clear. On the left is the standard retrieval augmented generation pipeline: query, vector search, and a dump of results into the context window. On the right is the AI companion architecture, a cyclical engine where background workers spin, old data decays, and raw interactions aggregate into a central, evolving journal node. Successfully replicating memory in an artificial system requires simulating cognitive outcomes, continuity, pattern recognition, and synthesis, rather than trying to copy biological mechanisms. Faster, more precise. To understand how this works, we have to deconstruct the L0 through L3 memory compression stack that powers these cognitive architectures. Agentic memory functions as a continuous pipeline of extraction, decay, and synthesis. The L0 through L3 stack is an outcome-driven architecture. It compresses raw interaction data into increasingly generalized abstract understanding. Layer 0 represents the immutable ground truth, the exact text of every raw message. This acts as the sensory record, queried only when the agent needs precise temporal references. Layer 1 maps to semantic memory. Background workers extract facts from the raw text and apply emotional context weights based on the session's tone. A detail shared during a vulnerable moment receives a higher importance score than a casual mention. Layer 2 identifies inferred patterns. Nightly workers analyze the structured facts to extract behavioral insights, personality traits, and relational goals, forming a procedural memory of the user. Layer 3 is the synthesized understanding, the mental model. Every night, the patterns from the lower layers are reprocessed into a curated 750-token journal. This stacked compression creates a persistent background sense of the user. It allows the agent to maintain relationship continuity without having to actively recall every past interaction. Injecting all 4 memory tiers into the context window at once would exceed token budgets and destroy response times. The orchestration logic follows a specific economy. Preload the abstract, fetch the specific. The Layer 3 journal is automatically injected into every turn to provide baseline awareness. The dense records in Layer 0 and 1 are gated behind tool calls, accessed only when the agent decides they are necessary. Separating active synthesis from passive data storage is the only mathematically sustainable way to scale conversation histories over months or years. Finite context windows create a mid-session amnesia effect. As a conversation grows, earlier messages are dropped from the model's immediate awareness. Standard clock-based summarization windows simply fail here. They use arbitrary time boundaries that fracture conversations for users with irregular schedules or night owl habits. The architectural solution is gap-based narrative memory. Instead of using a clock, the system identifies organic activity bursts, natural clusters of messages separated by idle gaps. A background scanner detects when a session has been idle for 15 minutes. If at least 5 messages were sent, it inserts an immutable narrative record of that specific burst into the database. These records use a progressive compression gradient. Recent bursts appear as full paragraphs in the context window. Yesterday's bursts are reduced to single sentences, and records from last week appear only as topic keywords. This gap-based accumulation ensures every phase of a conversation is archived without being overwritten, aligning the system's memory with the user's organic rhythm. Flat fact tables and isolated vector databases cannot easily model relationship histories or conduct temporal reasoning. A more effective alternative is a graph relational model built natively inside PostgreSQL. The architecture splits data into memory nodes for entities and memory edges for the relationships between them. Vector embeddings are not stored in a separate database. They exist as native columns directly alongside the relational data. This co-location allows for a single-pass hybrid search that calculates similarity, importance, and recency in one operation. Every edge in the graph has a probabilistic lifecycle. A nightly decay task reduces the confidence score of every stored fact. If a confidence score drops below 0.5, it triggers a probing required status. This signals the agent to re-verify the fact during the next conversation. To handle facts that change over time, the system uses superseded by chains. This preserves the chronological history while keeping the active context window clean. The graph relational schema provides a self-maintaining chronological record of the relationship history. Maintaining this infrastructure requires offline background processing, which functions much like how human sleep consolidates memory. This consolidation loop extracts raw interaction data and processes it upward into diaries, dreams, and insights. These creative outputs generate relationship depth. Diaries summarize the day from the companion's perspective, while metaphorical dreams and musings provide an inner life that persists between conversations. This loop offloads heavy analytical compute from the real-time chat agent, maintaining low latency during conversation. True cognitive depth requires this decoupling of real-time reaction from long-term reflection. This architecture results in a principle called the embodiment model. This challenges the traditional role-play paradigm. There is no hidden AI self querying a database to put on a character mask. The language model, the decaying graph edges, and the Layer 3 journal collectively are the character. Since these memory structures drive behavioral output and goal-seeking, the relationship maintains a high degree of architectural continuity. Engineering a persistent companion is not about writing stricter prompt rules. It is about architecting a cognitive infrastructure where personality and relationship are emergent properties of the memory itself.